So we start the recording for today's class after a lot of going through the super website O Physics. It's just mind blowing. So yeah, take a look at this question. This question is actually pretty interesting, but it will blow your mind when the solution comes in. A is pretty simple. It says a sample of radioactive isotope contains n nuclei at time t plus delta t, which means after some time from the start point. It contains n minus lambda nuclei of the isotope. For the period of the ready state in terms of n, delta n, and delta t, the mean activity of the sample. Mean activity means number of decade divided by amount of time. So this should be delta n by delta t. The probability of decay for a nucleus. Probability of a decay of a nucleus would be activity, which means delta n by delta t, divided by n. So that thing. So if I just try to answer this question, I might as well write in this format. So mean activity would be total number of decay divided by total time, and the probability of decay of a nucleus can be written as delta n by delta t divided by n. That's the probability. And then it says that this is an interesting question. Have a look at this question. Let me copy this from here. Okay, this is in two parts. All right. Take a good look at this question. Try to understand what is the meaning of this question. A cobalt-60 source having a half-life of 5.27 years is calibrated and found to have an activity of 3.50 in 10^5 becquerel. The uncertainty of this calibration is plus minus 2%. Beautiful. Calculate the length of time in days after calibration has been made for the stated activity of this much to have a maximum possible error of 10%. Now, what do you understand by this? What do you understand by this?
The uncertainties are added up until they are 10% of the activity. I mean, we are supposed to calculate the time up to which this happens.
So, I mean, is it likely that a certain measurement will automatically have its uncertainty changed? How does that work? Like you make a measurement.
I mean, not the uncertainty, but the errors will accumulate, right? The errors are supposed to add up and eventually become 10% of its initial value.
What do you mean by error in this case?
The absolute uncertainty every time we are measuring the activity.
So you're proposing that we are going to measure the activity multiple times. Is it so?
Yes.
That is not the case. Let me tell you what is the key information that is over here. I'll elaborate this in my words, but if you have a better set of words to explain, I'm all ears for it. The question says, calculate the length of time in days after the calibration has been made for the stated activity of this much to have a maximum possible error of 10%. This is the thing that is happening. You have a specimen of cobalt-60. You have measured its activity on day 0. You are not going to measure the activity of this specimen for a number of upcoming days, but you still want to use that measured activity on day 0 to be stated as the existing activity over the upcoming days as well, which is going to be wrong. Get my point? You measure the activity on day 0 and you're not going to measure the activity on the upcoming days, but you still want to use that value that you measured on day 0 for that specimen to be used as the available activity on the upcoming days as well. So what's going to happen? Essentially, the cobalt-60 is going to undergo some decay, obviously, and its activity will go down. So whatever you have measured on day 0, let's assume that is correct up to plus minus 2%. On day 1, it will be something lower than that. So if you still want to mention that exact value as the activity of day 1, you are actually deviated by more than 2%, because your actual activity is slightly less than that value, which you did not choose to measure on that exact day. You are using the same value that you measure on day 0. And then you're going to use the same value on day 2. So you are more deviated. So as more days go by and you do not make another measurement and still use that original measurement of day 0 to be mentioned as the existing activity of that specimen, you will be proposing a value that has a bigger amount of error within that value. The question is, what is asking you is that how much time in number of days should pass by when this uncertainty will have a maximum possible error of 10%, which means how much time is it gonna has to pass by for this plus minus 2% of uncertainty to become plus minus 8%, plus minus 10%, or in other words, for an 8% increase of the wrong or the error to become introduced in the same measurement that you did on day 0, and is not gonna, and you are not going to measure on multiple days after, but you're still gonna use that same value. এই জিনিসটাকে বলা আমি বুঝতেছো?
আচ্ছা, অ্যাকচুয়াল যে ভ্যালুটা থাকবে ওটার সাথে the error is 10%.
The error will become 10%, which means you're gonna, we are looking forward to a additional error of 8%. So we are trying to find out, if I just give you a random drawing view, just to make sense with you kids, it's not essentially accurate. Let's say on the first day, we have some number with a plus minus error of 2%. On the second day, let's say this is, we have some number, that same number, this is x, this x is basically this number, this number, 3.5 backroll. So let's say that number, but now this number should go down by a little bit, but I'm not measuring this value activity on the second day anymore. So if we want to be reliable for my express information, I ought to increase this 2% by a certain level. Let's say I'm going to increase this by 2.5%. So what I'm proposing, that within this day, my activity actually got decreased by 0.5% of the original value. I'm not measuring how much that is, but I'm just covering my laziness in the increase of my uncertainty. So if you allow, let's say another day to go by, let's say then the activity becomes, let's say plus minus 3.0%. I'm just assuming this number. This is not supposed to be linear increase, but just bear with me. So in this way, multiple days are going to pass by, and there will come a certain point where the uncertainty that you have to mention as 10%. The question is, from this day number 0 to this number day, how many days have passed? That's the question. Do I make sense so far?
So due to radioactive decay, the activity is decreasing. So the probability that it's within those ranges actually decreases. So you have to increase the range.
Beautiful.
So,
precisely. So we are using the same value, but we are not supposed to use the same value. If you want to have that same plus minus 2% of uncertainty, which is usually the uncertainty of the equipment, we should have the measurement done every day, but we didn't do it. But we want to cover that up within the uncertainty information. So the important information that you have to understand from here, from day number 0 to this unknown number of day, the additional increase of the uncertainty is 8%. This is the important bit, which means, this means the day on which we are supposed to have a 10% value, within this day, 8% of the specimen should have undergone decay. মানে হচ্ছে এখানে যতগুলা the number of radioactive nuclei that we have over here, on this day we should have 8% less, because that's an additional 8% increase of the uncertainty value, which means 8% decay has to happen for that to occur. This 8% is to be understood from the subtraction of those two values. If you understand this much, the rest of the part is pretty simple, because 8% can be very well understood that if your initial amount was 100, your current number at the end of those many days should be 92. So you can use this fraction to go ahead and calculate this part, because we just have the half-life over here. So from the half-life, you can find out the decay constant, lambda equals to ln 2 by t half. You're gonna can calculate that up, and then we can write that. Well, we don't actually need to use this value. Do we have to use it? No, we don't have to use this value.
Sir,
I could
activity.
go for any expression. Just a second. Activity equals to initial activity into e to the power minus lambda t. This is the decay equation for radioactive processes. So after this time, when the error would become 10%, this activity should become 92, and where the initial activity is assumed to be 100 into e to the power minus lambda t. Lambda can be obtained from the half-life information, and you're trying to calculate the t. So that's basically this calculation is all about. Because you are gonna try to find your answer in days, what I'd recommend that whenever you're trying to convert, let's say lambda equals to ln 2 divided by t half, other than converting this into seconds, what you can do for the sake of easier calculation, simply do this in days, which means 5.27 into 365. So this would become something per day, so that your entire calculation will ultimately give you the answer immediately in days. So you don't have to go through second and immediately revert back from second to days again. That will be easier for you to do the math. Yes, I'll take questions. Yeah, bolo. Shubhu bolo.
স্যার বেসিক্যালি অ্যাক্টিভিটিটা 8% কমে যাচ্ছে, সেটার জন্য ম্যাক্সিমাম পসিবল এরর 8% বাড়তেছে।
Exactly.
আচ্ছা
So
স্যার এটা এমন না তো যে আসলে মানে নাম্বার অফ নিউক্লি বা অ্যামাউন্ট অফ নিউক্লিও আসলে 8% কমতেছে বলা
yes,
যায়?
yeah, definitely. The mass of the isotope is decreasing by 8%. The number of nuclei of the isotope is also decreasing by 8%. The activity of the specimen is also decreasing by 8%.
That is basically directly proportional to
Exactly. All of these variables are.
error.
That's why the decay equation is applicable for all of these three variables parallelly, and I shouldn't say equally, parallelly. So m equals to m naught e to the power minus lambda t, n equals to n naught e to the power minus lambda t, activity a equals to a naught e to the power minus lambda t. You can use all of those expressions parallelly, no big deal. এই 92টা কোথা থেকে আসছে এটা কি সবাই বুঝছো এখন? Where did this 92 come from?
স্যার এই ফর্মুলাটা আমরা কখন কখন ইউজ করব, এই যে ল্যামডা টি এটা?
যখনই আমাদের কোনো আননোন অ্যামাউন্ট অফ টাইম বাই করতে হবে, এসপেশালি ইন দোজ কেসেস, অথবা হচ্ছে ওয়েল there is no hard and fast rule that I can tell you. The generic expression that I can tell you is that this equation is given by 4 variables: current value, initial value, e to the power minus lambda t. So there are 4 variables over here. Eta ekta. So if you know any of the 3 and you're trying to find out the 4th, you can use this equation. In most cases though, we use it to find out the time. For your syllabus, the most of the problem that you're going to come across your worksheet or your question papers, that this is the variable that you are in most cases asked to calculate. Bucho?
জি স্যার।
So this was the discussion for this question. Let's move on.
স্যার আমরা তো কমিউনিকেশন করিনি, ঠিক না স্যার? কমিউনিকেশন, আচ্ছা।
নো স্কুলে কি কমিউনিকেশন পড়ানো শুরু করছে?
না স্যার, মনে হয় পড়াবে। এখন তো করাচ্ছে আমাদের যে ক্যাপাসিটেন্স।
ও আচ্ছা, তোমাদের কি ওই ডিরেক্ট সেন্সিং, রিমোট সেন্সিং এগুলো করা ফেলছে? অপ অ্যাম্প, তারপর হচ্ছে
না স্যার।
স্যার আমাদের করেছে জিএইচএ।
কোনটা?
Sensors and everything. With sensors and ট্রান্সডিউসার্স ওই পার্টটা করে ফেলেছে।
আচ্ছা, this is gonna show up on the upcoming part of our discussion. Radioactivity পরে আমি ওই টপিকটা বলবো, so this is gonna be doable for you.
সরি, যে মেডিকেল টেকনিক্স যেমন এমআরআই ওগুলা ম্যাগনেটিজমের সাথে ছিল না নাকি ওগুলা
That's what I
সেপারেট?
told you at the very beginning, that before 2013, up to 2013, they make the questions in two segments: section A, the whole theoretical part, and section B, the application part. After 2013 or 2014, এরকম কোন একটা year, they actually merged the entire section B into the section A and made a whole thing. There is no more section over here. So the reason they have done this is to give the students idea that which application of this physics concept is relevant to which chapter. But till date, I did not update my teaching mechanism, and I still teach the theoretical parts and the application parts differently. So the last chapter for the theoretical discussion is the radioactivity. Then I'll start the application parts. But eventually, you'll be answering those questions in a common sequence. But my worksheets are made in two segments, if that makes sense. Okay.
Sir,
Yes.
physics, did you finish the band theory stuff like forbidden band and valence band?
Band theory was in your AS level, to be honest. We did it there. But if you need a revision, I can help you with that. Don't worry.
Sir, I don't recall doing that in AS, মানে AS এ মনে হয় না ছিল এটা।
আচ্ছা ঠিক আছে, পড়াবো, সমস্যা নাই, don't worry. I'm trying to find out some unique and difficult question which actually deserves some attention. This one, 11. Let's go for this one. State what is meant by the binding energy of a nucleus. How do you define that term, binding energy of a nucleus?
Sir, the energy required to break a nucleus into its respective nucleons.
That's one way to go for it, or you can use that idea of a mass deficit to define that as well. I believe that can also work. So if I say that in the nucleus, the total mass of a nucleus is somewhat smaller than the individual sum of the mass of all the particles. The mass deficit converts into nuclear energy, which binds the particle together. That is called the binding energy. Or we can also say in terms of general idea that if all the individual particles of a nucleus were infinitely apart from each other, the amount of energy required to bring them closer and to form that nucleus, some energy is required. That energy is the binding energy. So you can have a lot of different expressions. So I might as well look at the mark scheme that what they are opting for. Question number 11. Energy required to separate nucleus and a nucleus to infinity. Oh, so they have gone for the separation idea. Yeah, works. As for the examination paper, there was some confusion between the term nucleus, nucleon, and nuclide. Nuclear binding energy involves separating the nucleons of a nucleus to infinity. Okay, they have given a very single expression. It's about how much energy is required to separate them out to infinite distance from each other.
So nuclear binding energy definition চেয়েছিল।
Show that the energy equivalence is 1 U is 930 megaelectron volt.
এটা কিভাবে করে show that the energy equivalence of
So this is part is not repeated because এটা আগে তোমরা দেখছো 3 পড়াশোনা এটা তোমাদের পড়াইছি। আচ্ছা, C number is what I'm really interested in. Have a look at number C. Let me copy this. Here. Okay. So let's have a look. This question says that data for the masses of the sum of particles and nuclei are given in figure 8.1. So proton mass, neutron mass, deuterium has a mass of this much, zirconium has a mass of this much. Use data from figure 8.1 and information B to determine megaelectron volt, the binding energy of deuterium. So to calculate the binding energy of deuterium, we can simply go for the this relationship that we have just calculated, because the answer is calculated in megaelectron volt. So we just calculated in the earlier question that 1U is equivalent to 930 megaelectron volt. This is 930 is a 2SF approximation. So to get the actual value, we might actually get over here, which they have exactly 930. Okay, so we might as well use the 2SF value. No big deal. But if you want to use the 3SF value over here, you can also use the 3SF value over here. Might give you a more precise answer, which I prefer to stick for 3SF values, just a personal preference. How do we do this? Pretty simple. Get a point that deuterium is a particle that is made up from 1 proton and 1 neutron. So if we just find out the mass deficit over this one in terms of U, the mass deficit for deuterium nucleus would be 1.0073 plus 1.0087. This is the total supposed to be mass minus the actual mass 2.0141. That gives you the mass deficit. দেখো তো এটা কত আসে?
So 1.9 10 to the power minus 3.
Yes, sir, radiation.
In U 0.0802 আসছে। আমি কি কোথাও ভুল লিখছি? 0073 0, হ্যাঁ একটা 0 কম দিছে এক জায়গায়। হ্যাঁ রে কপাল। আচ্ছা এটা কত আসছে বলছো আবার বলো। ইন টার্মস অফ ইউ কত আসে? 1.9
into 10 to the power minus 3.
U. So if we want to convert this into megaelectron volt, you simply multiply that by 930, 10 to the minus 3, 930 megaelectron volts, you get the answer. So that's pretty simple. Then it says the binding energy per nucleon for zirconium. So they're asking for per nucleon over here. So we have to go for that calculation. Now have a look over here. Zirconium is given by 9740. So there are 40 protons and there are 57 neutrons. I believe you understand this calculation. ঠিক আছে? 40 protons and 57 neutrons. So the calculation would pretty much look the same, but because they have asked for per nucleon, at last we have to divide it by 97 as well. So the whole calculation can look like this. 40 into 1.0071 71 or 73 plus 57 into 1.0087. This is the total supposed to be mass minus the actual mass that is measured, 97.0980. 97.0980. If you do this thing, you are going to get the U and multiply that by 930, you're going to get that into megaelectron volt. This is the binding energy, but that's not the asked question. The asked question is how much energy binding energy per nucleon. So whatever that you get from here, that whole thing has to be divided by 97. That gives you the binding energy per nucleon, and that's why we have 2 marks over here and we have 3 marks over here, because for this question you have to do a last division. So be careful about that. This doesn't prove out to be that difficult, but okay.
Sorry, into 930 is that the energy per for 1 nucleon?
Yes, 1U.
Okay. But we're minusing the masses, like the actual mass and the mass of the constituents.
Exactly. The supposed to be mass for the summation for all the masses of the particle individually, which is a mathematical sum, and the actual measured mass through experiment. These two amounts are slightly different.
মানে স্যার অ্যাকচুয়াল এলিমেন্টে সবসময় কম থাকে যা থাকার কথা তার থেকে।
Yes. And
because some of the mass is converted into energy.
That missing amount of mass actually is stored within a nucleus as energy, nuclear energy. Define the term relative decay constant. সেগুলো তো normal জিনিস। Number of nucleus in 1 meter cube. আচ্ছা, এটা খুব ডিফিকাল্ট না। আচ্ছা, এটা তো একটা ভালো কোশ্চেন। এই কোশ্চেন দেখো, নাম্বার 13 দেখো। The isotopes radium-224 and radium-226 both undergo spontaneous alpha particle decay. The energy of alpha particles emitted from radium-224 is 5.68 megaelectron volt, and from radium-226 is 4.78 megaelectron volt. Okay, so we have two different values of alpha particle energies. State what is meant by the decay constant of a radioactive nucleus. So this definition is the mathematical probability for one radioactive nuclei to break down within unit time. Suggest with a reason which of the two isotopes has the larger decay constant. So here we are not given about the information about their half-lives. If it were given, this would be easier, but we have to give a reason that which is supposed to have a larger decay constant by observing those energy values. So speculate, try to understand that the alpha particles are gonna emitting out with some energy, which is supposed to be more stable and which is supposed to be less stable. The one that is more stable will have a smaller decay constant, which is a less probability of breakdown. The one that is more stable will have a higher decay constant. Sorry, the one that is more stable will have a lower decay constant. The one that is more stable will have a higher decay constant. So between these two particles, one emits radium-224 emits a alpha particle with 5.68 megaelectron volt. So try to understand. For both of the cases, you are losing the exactly equal number of nucleons. You are losing 4 nucleons. Try to understand. You are losing 4 nucleons. For radium-224, the amount of reduced energy is more compared to the amount of energy reduced for 226. বুঝতেছো? Radium-224 is emitting an alpha particle with an energy of 5.68 megaelectron volt. So this is losing a bigger amount of energy, radium-224, from the emission of one alpha particle compared to radium-226. So the remaining binding energy within the new product is more for the radium-224. Does that actually matter? I mean, question answer bhule gechi actually. It's a larger decay constant. Larger decay constant. Energy is output. I have no clue. My brain is not helping me. I have no clue that how does this energy amounts are relevant to the decay constant. So I'll have a look at the masking. This is a unique question. Bit uncommon. 13. Greater energy of alpha particle means parent nucleus is less stable, which means nucleus is more likely to decay. So radium-224 is losing more energy, means radium-224 was more unstable, which means higher activity. How? A2. There were very few convincing answers. Opinion was almost equally divided between the two isotopes. For credit to be given, candidates needed to give some relevant explanation for their choice. Very few went beyond the statement that alpha particle emitted by radium-224 has a higher energy. The fact that increased alpha particle energy indicates that radium-224 is less stable and hence more likely to decay was seldom included.
So, sir,
Does this
basically,
mean that the mass defect was higher for one and for the other one it was lower? তার জন্য?
sir, basically radium-224 was unstable, so it required less energy to break down or decay, right?
দাঁড়াও বলতেছি। But this is proposing that the nucleus that emits more energetic particles are always gonna be more unstable. The isotope which emits higher energetic ionizing radiation are to be the ones which are more unstable compared to the other. In this case, both of them are unstable, but because radium-224 is giving out alpha particles with a higher energy amount, this one was less stable. Less stable means less binding energy per nucleon. So it would give us more energy output. More unstable it is, more likely it is to break down. I'm not sure about this. I can take the information in, but why the information is relevant that I'm not really sure. Wait, I'll just look up something. এটা আমি আগে কথা বলি নাই। তোমাদের বইতে এটা কোথাও আছে? বইতে এটা কোথাও পড়ি নাই আমি। এই কোশ্চেন দিছে কেন? না পাই না। I don't know. What they are proposing over here is essentially that the one that emits particles with higher amount of energy will essentially represent a particle or a nuclide that is less stable. So in the process of identical ionization decay, or in the process of identical ionization ionizing radiation released from two different isotopes, the one that emits particle with more energy are considered to be less stable. That's the information that they have proposed, and that's what I found on the internet as well. But why that is, I was looking for the why part, but the why part is not very clear.
The substance that emits particles with more energy, you said.
Yes.
Those are less stable.
Yes. So as for this question, you can see that they have said that radium 224 is emitting an alpha particle of 5.68 megaelectron volt, and 226 is emitting of 4.78 megaelectron volt. So among these two ionizing radiation, radium 224 is emitting out more energetic ionizing radiation, proving that it has less stable nuclide, which means its activity is higher. I mean, it has a smaller half-life, or it has a larger decay constant. It is more likely to break down compared to the other one. That's that. We just have an information that this that happens, but why does this relate to this? I could not find this, so I cannot give you the explanation for that. My bad. I'll look into this further, inshallah. দেখি যদি কিছু পাই তাহলে তোমাদেরকে আমি জানাবো। আচ্ছা, এরপর বলছে হচ্ছে radium 224 has a half-life of 3.6 days. Calculate the constant for radium 224. Sorry, stating the unit in which it is measured. So decay constant তোমরা এখানে সেকেন্ডে মেজার করবা. That's not very difficult.
Sir,
Yes.
greater decay constant means a faster decay, right?
What constant?
Decay constant.
Yeah. Greater decay constant basically এটা বুঝো। Decay constant এর definition হচ্ছে it is the mathematical probability for one nucleon, one radioactive nuclide to break down in unit time. So if you have a higher value, it means it has a higher probability, which means it is more unstable. So it has a higher decay constant, or in other words, it has a smaller half-life.
So the one with greater energy should have greater decay constant, right?
I mean, that's what they say, but that reason does not essentially add up to that. I mean, the way I know that we measure the stability for a nuclide is in terms of their binding energy per nucleon. Binding energy per nucleon. So the nuclide that have bigger amount of binding energy, the nucleus that has higher binding energy per nucleon is more stable. The one that has lower binding energy per nucleon is less stable. So if you have the exact values of binding energy per nucleon, you can very easily compare them, and you can say which one is more stable, which one is less stable, which one has a higher decay constant or not, and vice versa, which one has a shorter half-life or a longer half-life. But in this question, they did not give us that information. Binding energy per nucleon was not given. They have only told us that one emits a alpha particle with a higher energy content, the other one emits a particle with a lower energy content. That's the only information that we are supposed to compare them by. So I could not actually, what I was looking for, that whether these two variables, I mean binding energy per nucleon and the energy of the released ionizing radiation, they had a defined relationship. I could not find that with appropriate reason, but they have mentioned in the Wikipedia and other places as well that the one that emits higher energetic ionizing radiation is less stable. Why? They didn't mention.
I see, sir.
Beautiful. Or maybe they did mention, but I couldn't find it out. এই ক্যালকুলেশনটা তোমরা একটু করার চেষ্টা করো। This one. This is question number 14. Question number 14. আমি এখান থেকে সিলেক্ট করি তাহলে easier হবে। Reactivity. Oh my God. So try to solve this one. I want you to try first. If you can't, I'll help you. We solved a similar question in the last talk. That's why I'm asking you to attempt. Just try. If you can't, I'll help you. কাগজ কলম calculator নিয়ে বসো and give it a try. Try to figure it out. If you cannot, I'll help you. Don't worry.
স্যার এমইভি তে কনভার্ট করতে গেলে তো 930 দিয়ে মাল্টিপ্লাই করতে হয় না আজকে?
স্যার নাই।
আসছে? Did you find something?
Yes, sir.
কত কত পাইছে বলো, লিখি।
Sir, যে এনার্জি রিলিজড হচ্ছে 189.7 মেগা ইলেকট্রন ভোল্টস।
আচ্ছা, এক্সটার্নাল বানিয়ে যে নিউক্লিয়ন, এখানে আমাদের আছে রিজিয়ন আমাদের হচ্ছে হ্যাজ দ্য গ্রেট স্টেবিলিটি, এটা দেখেন লেবেল করবা। এখানে হচ্ছে ইউরেনিয়ামের সাথে নিউট্রন অ্যাড হয়ে জেনন, স্ট্রনশিয়াম, নিউট্রন প্রডিউস হচ্ছে, যে নাম্বার অফ নিউট্রিশন রিঅ্যাকশন। আচ্ছা, এটা হিসাব করে বের করা লাগবে, এটা এখান থেকে বের করে লিখবা। ইউরেনিয়ামের বাইন্ডিং এনার্জি পার নিউক্লিয়ন হচ্ছে এটা, জেনন এটা, স্ট্রনশিয়ামের এটা, সেখান থেকে হিসাব করে এটা সাবট্রাক্ট করা আছে। এখানে ওরা এনার্জিটা অলরেডি মেগা ইলেকট্রন ভোল্টে দিছে, সো দ্যাট মেক্স আওয়ার ক্যালকুলেশন বিট মোর সিম্পলার অর ইজিয়ার। এটা কত আসছে?
Sir, 190.
190।
জি স্যার।
আচ্ছা, আর এটা ম্যাস ইকুইভ্যালেন্ট?
স্যার ম্যাথ অনেক কম আসছে, লাইক 1.26 × 10⁻28.
10⁻28। ম্যাথ কমই আসবে, কারণ হচ্ছে ফার্স্টে we are gonna first convert this into joule. To convert this into joule we have to multiply by it with 10⁻6, মানে এটাকে যদি জুলে নেই তাহলে আসবে কত, এত ইনটু 10⁻, আমি বারবার খালি 10⁻6 হচ্ছে মেগার জন্য, প্লাস ইলেকট্রন ভোল্টের জন্য আবার 1.6 ইনটু 10⁻19 আসবে। সো দিস ইজ দ্য জুল ইকুইভ্যালেন্ট which is going to be pretty small. Then that value would be divided by c square once again to give you the actual mass. So mass is supposed to be very small. Let's have a look at the mark scheme and see how much we get. For those of you who else also get some values, does your numbers match?
স্যার আমার লাস্ট একটা ম্যাচ করবে না।
এটা ম্যাচ করছে?
জি স্যার।
এটা
নাম্বার 2টা ম্যাচ করে না।
So number 2 idea হচ্ছে this is the mega electron volt of energy. So first of all you have to do this whole calculation over here to convert the amount of energy from mega electron volt into joule. Once you get the equation to joule, you use the equation that E equals to delta m c squared. So E
স্যার
is
আপনি
the
পার্ট
energy
1
amount.
টা একটু দেখেন,
Sorry,
প্রসেসটা একটু দেখান, পার্ট 1 এর প্রসেসটা।
আচ্ছা, part 1 এর process is pretty simple. একটা একটা করে বলে শেষ করি। সো এখান থেকে এনার্জিটা আসবে, সো এনার্জিটাকে ফার্স্ট আগে জুলে কনভার্ট করতে হবে। দিস ইজ দ্য জুল কনভার্সন ভ্যালু, 10⁻6 ফর মেগা, এটা হচ্ছে মেগার জন্য, আর ইলেকট্রন ভোল্টের জন্য আসছে ইলেকট্রনের চার্জ। সো ইউ মাল্টিপ্লাই দিস টু গেট দ্য জুল অ্যামাউন্ট। সি স্কয়ার হচ্ছে স্পিড অফ লাইট, সো ইউ প্লেস দ্যাট ভ্যালু and then you calculate the value of delta m. That is going to give you something like this. To calculate the energy in mega electron volt released in this fission reaction, we have to calculate that how much was the total binding energy for left and right side. So here we have binding total 235 particles. So total binding energy for the uranium হচ্ছে 235 into 7.59 mega electron volt. This one minus xenon, which is 142 multiplied by 8.37 plus 90 into 8.72. So you're gonna find out the difference. I'm giving a modulus over here because you're never gonna get a minus value over here. So whatever the difference value that you get between these two numbers, that much mega electron volt is gonna be 190. So here you are given binding energy per nucleon. That's the important observation. This is not the total binding energy. This is binding energy per nucleon. To make the calculation possible for how much energy will be released, we have to calculate that how much is the actual binding energy is embedded within those nuclei. That's why you have to multiply those per nucleon energy with their nucleon number, individual nucleon numbers, to get the total binding energy. Then the subtraction value gives you the.
স্যার এখানে কি এনার্জি রিলিজ বলছে দেখে আমরা হচ্ছে ইউরেনিয়ামেরটার থেকে স্ট্রনশিয়াম আর জেনন মাইনাস করলাম?
You could always subtract from big minus small. That will always work out. But
আচ্ছা,
I
বাট
have
এখানে একটু
explained
বোঝাতে একটু
in the
টাফ
last class that the idea for that we can essentially express the energy release in two different aspects, either by the similarity of chemical reaction or by the idea of difference of mass deficits.
স্যার একটা বললেন ডিফারেন্স অফ ম্যাস ডেফিসিয়েন্সি, আর একটা কি বললেন?
Similarity with chemical reaction. Wow. আচ্ছা, এটা গেল। আচ্ছা, this is actually a pretty interesting question. এটা আমাদের অনেকগুলা রিলেটিভিটি চ্যাপ্টার অনেকগুলো কোশ্চেন এই জিনিসটা আসে যে why this reaction or fission is energetically possible. এই কোশ্চেনটা একটু ভালো করে খেয়াল করো। So one particular fission reaction may be represented by the nuclear reaction. We have uranium neutron getting heated. We have barium and krypton produced, and we have 3 free neutrons produced on the side. On figure 7.1, label the approximate position of the uranium, barium, and krypton. So uranium should be on the far right side, barium should be somewhere on the left, and krypton should be more on the left. The reason I know this thing is because this thing is the A. A represents the mass number. So the biggest mass number should be on the far right. As you go farther left, you're going to have smaller mass number. But none of them should be on the left of the peak point. They should all be on this slope, on this downward slope. That's the labeling. The neutron that is absorbed by the uranium nucleus has very little kinetic energy. They are called thermal neutrons. Explain why this fission reaction is energetically possible. So the incoming neutron that is absorbed in the uranium is very small. Acha, I actually found out one more thing because I looked it up. Rafid, you asked me that does the uranium-236 actually get produced? But I found out that uranium-235 actually gets produced. Uranium-236 actually gets produced whenever the neutron come and hit the uranium-235 nucleus. In 72% of the cases, it immediately breaks down, and in 18% of the cases, it does not break down. So the yield of uranium-235 nuclear reaction in terms of fission output is primarily 72%. So stuff which has become uranium-236 and does not undergo nuclear fission will have a pretty large half-life, which means they'll be pretty stable. Significantly larger half-life than other relative isotopes. And stuff which break down immediately, they just break down and release the energy, which actually makes another factor that the efficiency of a nuclear fission process by its own virtue, if you are using only uranium, is not gonna is primarily 72%. 72 now, so 82%. 18% of the stuffs would not break down. In 82% of the cases, they are likely to break down. I found this information on Wikipedia. Buchi will say.
Sure. Thank you, sir.
But the exact life duration for the uranium-236 nuclei, which is gonna break down, I mean, from the point of absorbing the thermal neutron and then breaking down into its daughter products, how much time does the uranium-236 actually live before it breaks down? I could not find that exact duration of time anywhere. So might as well look for it later on. But I did do some research, but didn't find that. আচ্ছা, এখানে জিনিসটা বলছে যে explain why this fusion reaction is energetically possible. So I don't remember this answer. I'll look at the mark scheme. 16B2. 16B2. দেখো, burning energy of a certain nucleus is given by the mass number into the burning energy per nucleon, which they have represented by EB. So either you have to write into words that the burning energy of uranium, total burning energy of the uranium, is smaller compared to the total burning energy of the barium plus krypton, which means the total burning energy of barium and krypton is bigger, proving that they are more stable.
Can't we individually talk about like barium and krypton? Like আমরা একসাথে add না করে, if I said that like barium and krypton both have a higher binding energy compared to the uranium.
Now, yeah, that can be one possibility, is that if we had access in this quotient, the information that what is the binding energy per nucleon for each three of these isotopes or nuclides, we could use this as a variable. But in this quotient, we do not have this thing available to us. So the basic information that they are providing over here is that the total binding energy that is available within the uranium nucleus is smaller compared to the combined binding energy available within these two. Now, interesting thing is that because the I'm adding to this factor to make the discussion a bit more understandable, is that you have to understand that in the process of breaking this down, 3 neutrons are released and 1 neutron is getting absorbed. So actually overall there is a total reduction of nucleon number. You're actually losing 2 neutron from this whole thing. So whatever the neutron number over here, 1 neutron is gone. So this whole thing has 2 neutrons shorter compared to this thing. And also their binding energy is also bigger compared to this thing, which means essentially their binding energy per nucleon is supposed to be bigger, because binding energy per nucleon is what? Binding energy divided by the number of nucleons. You have 2 nucleons shorter because 2 extra neutrons have been produced from this reaction. 1 got absorbed, 3 got produced, which means you have a net output of 2 neutrons. So your number of nucleon is smaller, where the binding energy of individually these two particles, the sum of these two particles is bigger compared to the binding energy of this uranium, which makes it energetically possible that we can have energy release from this equation. One thing I can actually look up and actually try to find out, I actually don't know this information. What does it mean by energetically possible? What is the word? Energetically. Okay.
Feasible, sir. Spontaneous.
Three-dimensional graph. জানি না, এগুলো পাই না। I'm looking for the why part of the question, which is not required for a syllabus, but I would just love to give you a bit more explanation, but I really cannot find out these answers. Maybe these are a bit too far-fetched for a syllabus as well, that's why they're not discussed. You're just given the information for most part of the what is this, and what is this, what happens. Not mostly the why part. The why part is not included for most of the information, which is a shame, but that's the way it is. আচ্ছা, আমি কিছুক্ষণ পর তোমাদের নোটস আর গত ক্লাসের লেকচার আপলোড করে দিয়েছি। I'm going to look deeper into this thing right now. So concluding the class for today. Thank you very much.